Okay, welcome to lecture 10. So we didn't have class Friday, so today we're going to start something new, which is the chapter on classification. Actually, chapters 4 and 5 are both on classification. I'm going to do some of both of them. Chapter 4 deals with basic classification, defines the problem, talks about decision trees, and then chapter 5 gets into some of the more modern techniques. So we'll start with chapter 4 initially. There is a new homework if you're interested in playing along with the homework that's posted on the web page. But I'm just going to start into chapter 4. The main concepts here are talking about what the classification problem is, how you fit decision trees, and how you validate models. Then in chapter 5, we'll talk about some more modern approaches. The what do you want?
Oh, it is.
It's on.
Okay.
Yeah. So if you think about the classification game, generally you have a training data set and a test data set, and the test data set is unlabeled. Now, what I should say, though, is that often this distinction is artificial because what you do is you always want to know how well you're going to do on new data. You don't have new unlabeled data, or if you did, you wouldn't know how well you're doing on it. So what you often do is just segment your data into a training set and a test data set and pretend the class label on the test set is unknown, and we'll talk about that in a second. But for now, let's just say I have a training data set and a test data set. And in this data set, you see there's 3 attributes, attribute 1, 2, 3. And the one that I'm really interested in predicting is the attribute here called class, okay? And so I have some sort of a learning algorithm, and then I learn a model. And what I'm doing is I'm trying to use these 3 attributes to predict the 4th one, the class, as accurately as possible, but not as accurately as possible on the training data. Of course, I want to do as best as possible on new data. So this is sort of a pictorial representation of what's going on. I learn a model on the training data, okay? Then for each one of these new observations, I can fill in the class based on the model I learned on the training data and see how accurately I can perform. So that's sort of the pictorial representation. To make it more precise, the classification problem is the following. Given a collection of records, which is my training data, each record contains a set of attributes X. Okay, so X's are your attributes, and of this course, this could be high dimensional. It could have a lot of different attributes. And then there's one particular attribute in particular that I'm interested in, which is the class Y, okay? And I'll talk about binary classification, so Y will take 2 values. You can extend most binary algorithms to handle more than 2 classes, but it is important that Y is categorical and not numeric. If Y is numeric, then we, of course, get into sort of a regression setting where we're trying to predict a numeric response. So Y is a binary class variable, and then we can extend the binary case into multiple classes. So we want to find a model to predict the class as a function of the values of the other attributes. Okay, so it's a prediction problem. We haven't done predictive modeling until now. We've always been doing descriptive statistics. This is a prediction problem. And the goal is that previously unseen records should be assigned as accurately as possible. And so how do we know how well we're going to do on previously unseen records? Well, again, we take some of our data. Sometimes you call it a holdout data set or a test data set. You leave it out, and then you see how well you can predict on that. So that's sort of a fair game because the model hasn't seen that data before. So you leave it out when you fit the model, but then to assess how well the model is doing, you fit to that, see how well you do on the test data set, and that tends to be a good metric for predicting how well you're going to do on new data. So it says here, usually the given data set is divided into training and test sets, with the training set used to build the model or learn the model or fit the model, and then the test set used to validate it or measure how well you're doing. So as an example, credit card transactions, right? You might have some data on previous transactions that you subsequently found out, oh, this was fraudulent or this was legitimate. So you look at all your X's, all the covariates, and then when you see a new example like that come along that your model predicts to be likely to be fraud, then you flag it as fraud, right? So when your credit card company calls you and says, we've noticed some unusual activity, unusual isn't their opinion of unusual, it's some classification algorithm that's identified that these covariates are predictive of a fraudulent transaction, so it gets flagged by the algorithm. Some example from chemistry, classifying secondary structures of protein as one of these 1, 2, 3 classes. Again, I'm going to talk about the 2-class problem, but you can extend those to 3-class and general K-class problems. Categorizing news stories as finance, weather, entertainment, or sports. So you can imagine applications of that. And then there's Arnold Schwarzenegger from Kindergarten Cop, right? Remember, he has the tumor, and he says it's not a tumor, but either it's I can't say that either, benign or malignant. Benign or malignant. Okay. So there's many algorithms for carrying out classification. This chapter, somehow we deal with decision trees. The question of why do we start with decision trees, it tends to sort of be, I think, more historically accurate, that's kind of the first algorithm that people started using for handling classification. It's certainly not the favorite algorithm anymore, but it is a sort of simple algorithm. It tends to be computationally efficient in some aspects and has some nice features. So we'll start with decision trees, but then in chapter 5, we'll start to study other techniques that are more modern and effective. And by saying that, it implies that decision trees are neither modern nor effective, and that's true to a large extent. I don't think that they're sort of the favorite algorithm of choice anymore, but in terms of going in chronologically and starting with something simple, we'll start with decision trees, and then we'll extend in chapter 5 to some more modern and effective techniques. So what does a decision tree look like? Well, obviously it looks like a tree, and so here's some data you might imagine where you're trying to predict whether or not someone's going to cheat on their taxes. And you have 3 attributes, so X has 3 components. It has whether or not they applied for a refund, whether or not they're single, married, or divorced, and then their taxable income, and then finally the attribute that I'm trying to predict, which is whether or not they're going to cheat. So how do I do this? Well, I take data from previous years, fit a decision tree to it, and then I can use that decision tree from previous years to predict data for future years. And if someone comes up as being predicted that they're going to cheat, then I can audit them, right? So how do you fit new data? Well, it looks like this, right? So a new observation comes along. This person did not want a refund, they're married, and they had $80,000 taxable income. So I want to know whether they cheat. So what I do, going back, right, I fit a decision tree on the data where I have the labels. I learn from the labeled examples, and when a new example comes along, I just sort of chase him down the tree, right? So this person, let's see, start at the beginning. At the beginning, you say, okay, did he request a refund, yes or no? And so this person did not request a refund, so he's going to go down this branch, okay? And then I ask about his marital status, right? Is he married or is he single and divorced? And this person happens to be married, so I follow him out here. And then the last thing to say is, well, that's it, right? Because he did not request a refund and he was married, so I conclude that he's not going to cheat. I didn't even have to look at his taxable income in this case, because knowing that he didn't request a refund and he was married is enough for this tree to predict, no, he's not going to cheat. Okay, so you just sort of chase them down the tree until you get to a terminal node, and then the terminal node gives you the prediction, one of your 2 classes, in this case either cheating or not cheating. Now one thing you'll notice about the decision trees is that in this case, right, I never use taxable income. And it's possible that you could have a lot of predictors that may never get used. So it does sort of some implicit variable selection for you, which can be very useful when you have a lot of redundant features and you don't know which ones of those features you want to use in your model. Okay, so if we're using R, the function R part, of course there's some other functions that fit decision trees, but R part in R tends to be the favorite these days. You should be careful when using this function though, because it also does regression trees, right? So a regression tree would be when you have a numeric response. And that can be problematic because you might think, oh, I think I'm fitting to 0, 1. I think I have a 2-class problem, and all of a sudden it gives you a prediction of 1.2. And you realize that our part is thinking that your 0, 1 is really numeric and just happens to take 2 values. I think it's actually even smart enough to give you a warning. Like, warning, I'm assuming that this is numeric, but I notice it only has 2 values. I think sometimes they'll even give you a warning. But to make sure that you're doing it right, of course, you want to make sure that your y is a factor, so as dot factor. And I quoted a little bit of a note here from the help. It says, if y is a factor, then it will assume method equal class. So of course you can force it to say method equal class, but by default it's going to look at what type y is, and if y is a factor, it assumes you're trying to fit a decision tree, which does classification, as opposed to a regression tree, which fits to a numeric response. And you can imagine things are slightly different. You have a slightly different loss function. With the decision tree you get predictions that are either 0 or 1, whereas with a regression tree you get predictions which could be any value. Okay, so just be careful that you're telling R that you have a factor so that it knows you're doing classification, not regression, when you use R part, because R part does do both of them. Okay, so what does R part look like? Well, here is the text output from fitting a decision tree on some data that I didn't show you. And you can go through, I'm not going to go through all 3 of these, but you can chase it down and figure out what the prediction is. Of course, there's a function that does the prediction for you. I'm sorry I don't have black. If anyone has black, I'll use it, but I don't see any black. So I'm going to use blue. First person, age is middle, number equal 5, start equal 10, and we're trying to predict the presence or absence of this, I think it's a rare childhood disease. So what you do, you sort of chase this person down. So you start for A, this is a really bad marker, you start at node 1, okay, the root node, and all 81 people are there. And then the first thing it asks about, the indentation is meaningful here, right? Either the start is either greater than or equal to 8.5 or the start is less than 8.5. And this person's start is 10, right? So he happens to be up here. You know, start greater than or equal to 8.5. So from 1 you go to 2. And then the next question it asks, is it 4 or 5? Is his age old or young, or is his age middle? Okay? And it turns out this person is middle. So then I stay here at 5. Then after that, what do I have to ask? Oh, again, it asks about start again. So it's allowed to reuse the variable. And it says his start is either bigger than or equal to 12.5 or less. And start was 10, so that's going to be less. So I'm in node 11. And that is a terminal node. And I know it's a terminal node because it has a star by it. Right? Line 11 represents a terminal node, which has a star by it. And in there, there's 4 people. And 75% of them are present and 25% are absent, so he gets predicted to be present. So my prediction for this guy is that he is present. Present. Okay, so that's how you read the text output from R. I'll also show you what the graphs look like. But as you do this, it's sort of logical how you follow it down. You should also note that it does, some variables aren't included, some variables are used frequently, variables are allowed to be used more than once. It tells you at each stage, terminal nodes are with the star, but at any stage it tells you how many observations there are, what the majority class is, because that's what you would predict, and then how many are in each class, and then these 2 numbers are the probabilities. And this function works even if you have multi-class, right? It would give you all, if you had 3 different classes, it would give you all 3 probabilities. In this case, with just 2 classes, these 2 probabilities always sum to 1, but the function is flexible enough. If you had a factor with multiple levels, it could do multiple classes. So that's what the rpart function looks like in R. I'll talk a little bit about how it works, but that's how you read the text output. Any question about reading the text output? I think I'll just skip B and C. It's pretty intuitive. Okay, so let's fit it to some real data, well, real sort of in quotations. So you're all probably familiar with the sonar data. This is one of those classic machine learning benchmark data sets. It's a pretty small data set. I think it's like 208 rows and 60 predictors, and then the 61st column is the response. And where this data set comes from, there's 2 objects, right? A rock and a metal cylinder. And you bounce sonar signals off these 2 things, and obviously a human can label it as a rock or metal cylinder, but the challenge is to use the sonar signals to learn an algorithm that can predict accurately new objects as being the rock or the metal cylinder. Those are the 2 classes. So I'm going to look at, I split it into a training data set and a test data set. I think I put 130 observations in the training data set. Let's take a look at it. So here's the training data set. And yeah, I put 130 observations in the training data set, and then you can see there's 60 columns, which isn't really obvious in Excel since it puts letters, but then the 61st column is -1 or 1, rock or metal cylinder, I forget which is which. And so basically we're trying to use these 60 columns to predict the 61st column as accurately as possible, but not on the data that we're going to fit on, of course, on the new data. Okay, so that is the classification problem here. And so let's see here. How do we do this in R? Well, the first thing to say, again, rpart, which I'm going to use to fit my decision trees, is not in the base package, right? So you have to do, on Windows this works well, install.packages rpart. On Linux machines, sometimes you have to sort of download it locally and install it from a local directory, but this works pretty well on my Windows machine. I haven't installed packages on Linux in a while, so maybe easier now. Anyway, install.packages rpart. You only have to do this once, right? I mean, if you reinstall R, you have to reinstall the packages again, but you only have to do this once. But every time you want to use rpart, you have to read in the library. Okay, then this is a read.csv on the training data. Of course, there's no header, so I say header equal false, otherwise it's going to use the first row as the column names. Then y, the important part here is the as.factor. So I'm going to read in the 61st column as y, which is what I'm trying to predict, but as.factor y. So it's going to know that it has 2 classes, and in fact, the classes in that data were coded as -1 and 1. So let's see here. Where is R? There it is. File, change directory to, I think that's on my desktop. Let's see, there. Oops, I don't need to install it. Okay. There we go. And if you look at y, you see it's -1 and 1. And the key thing there is I know it's a factor because it tells me it has 2 levels, -1 and 1. Doesn't matter what numbers you use. If it's a factor, it'll adjust to those being the two levels. Okay, they chose -1 and 1. Some people like 0 and 1. Depends on who you are, what you're trying to do. Then X is the rest of the data, right? X is columns 1 through 60. And then here's the key, right? The syntax is R part Y, which is, of course, your response, your factor, your two-class vector. This is the tilde, and then dot, right? Dot just means everything, right? You don't have to write x1 through x6, you just dot. And then comma, the second argument is your data excluding your response. Okay, so that's the syntax that will fit a classification tree or decision tree, whichever you like to call it, as predicting y as a function of x based on all the default values, right? So just leave the default values here. We'll talk about what it's doing internally in a bit, but for now let's just take the default values. Presumably someone has tuned those to try and do a good job. And then the last line here, actually I ask you to compute the misclassification error. This would actually be 1 minus that. This would be the accuracy. And you can see, let's see, where did I'll just grab all this stuff again. So this last part should be intuitive to you, but I'll just mention. So on the training data, it's predicting with 88% accuracy, right? So the inside argument here, actually let me point on the slide, it's bigger. So this would just be y, right? That's the training data y. And then this is the predict function, right? The predict function takes the model object, the data that you want to predict, which if you wanted to predict for new data, you could put new data here, but I'm just trying to get the prediction from the training data. Type equal class, even though fit is, fitting with respect to a binary class label, if you don't say type equal class, you get probability outputs. And so I just want the class label outputs. So I say type equal class, and then I just divide by the length of y, which is 130. And I'll just show you what that predict function does. Predict is a very general function, and you can use it to predict from a lot of model objects. And it works in particular with our part here. So when I say predict fit x type equal class, those are the predictions from the 130 points in the training data. If I had left off class, it would actually give me the probabilities, right? The probabilities of the two classes for each observation. So by saying that, I get the class labels. And then in here you see the inside of this sum was simply a logical vector giving me true or false, whether or not the prediction observed with the actual value in the data. And then when I sum this thing, it sums up how many trues there are. And then I just divide by 130 to see that I'm getting 88% accuracy on the training data. Okay, so in other words, the misclassification error on the training data is like 11.5%. Okay, so that is the misclassification error on the training data. I want to make a note of it because we're going to compare some models. So this is number 33. This is the default call to our part with this data. And I got, what did I say, 11.5% misclassification error. So this is number 33. I said 11.5% was my misclassification error. 11.5%. That's on the training data, though, okay, which I don't really care about. Because the training data, I can just fit a really big tree, and I can always drive this down to 0, assuming that I don't have duplicate x values in there. So I don't really care what value this is. What I really want to know is how well this thing does on new data. So I read in the test data and do the same thing, but now I use y-test and x-test, and I look how often y-test matches the predictions for x-test as being the new data. Okay, so this is really the number that I care about to see how well it does on this new data, which I just sort of, held out from the fitting procedure, so the model hasn't seen this data before. And not surprisingly, I do worse, right? I have 69% accuracy, or another way of saying that is the misclassification error rate on the test data is 31%. So let's call that let's try the other one. Try that misclass, doesn't work at all. Okay, so call it misclassification error on the test data is 31%. So this is the default call to rpart function. If you know anything about the SONAR data set, it's commonly used as a benchmark data set. 31% isn't that good, right? You can beat that with some pretty simple algorithms, but by default, that's what rpart is giving us. Now, this whole split between the training and the test is somewhat artificial, and of course, you all know that there's other ways of doing that. Some people do cross-validation, some people use leave-out-1, things like that. But just to make it simple, I split it into 130 observations for training, and the other, I think, 78 for test. And that's one way of sort of determining how well we think how well the model will do on new data, assuming that new data differs in the same way as the training and test differ. Okay, so I think that's sort of the basic exercise that we go through in terms of fitting a predictive model for solving the classification problem and assessing how well it does. And so we can say the default call to rpart for this data is 31% misclassification error on test data. Okay, any questions about that? Okay, so let's experiment with the model a little bit. What if we were to say, instead of using, oh, you know what, I wanted to show you actually, sorry, let me go back a little bit. I do want to show you just what this tree looks like. So one thing you could do is say, what does it look like? Just say fit, and you can see it has 1, 2, 3, 4, 5, 6 terminal nodes. Okay, which predictors is it using? Well, it's not using all 60 columns. It's using V11, V27, V54, V8, and V52. So it's not using all of the columns, so it has variable selection built in with 6 terminal nodes, and remember it was getting about 11.5% misclassification error on the training data. So by default, R didn't grow the tree as big as it can. It stopped for some reason, and we'll talk about how it knows when to stop. But this is what the tree looks like. Another way to see it is to say plot of fit, and then that gives you a plot, and then you can add text to it, which you have to actually play a little bit with the default here in the text to make sure so the labels don't get cut off, but I'm not going to do that. Anyway, you can see there's other interfaces for plotting it better, but you can see how the tree looks, and it has 1, 2, 3, 4, 5, 6 terminal nodes, just like I said, and you can see here the variables that it's splitting on. Okay, so that's the default tree. So now suppose we wanted to try some other trees from rpart. So the first thing we might say is, well, let's try a really, really small tree. And let's try the smallest tree we can think of, which is a max depth of 1. So that's just going to split the terminal node into 2 parts. rpart only makes binary splits when it does each attribute. So we're going to do a max depth of 1, which means it's going to restrict to trees of depth 1, which will only have 2 terminal nodes, and see how well this thing does. So this is about the simplest tree you could think of. And here's the syntax for fitting that. You see that there's this rpart dot control. So I say control equal rpart. Actually, maybe I'll leave this up here a little bit more. I say the usual call to rpart, but then I say comma control equals rpart dot control. And if you do a help on this thing, you can see there's a lot of different defaults you can set. One of them is max depth, and I'm just going to set max depth to 1. So this is sort of the best default tree of depth at most 1, right? So do that, measure the accuracy on the training and the test data. And not surprisingly, right, the first number, we see 77% accuracy or 78% accuracy on the training data, which not surprisingly, you know, is worse than this one. So if we compare in terms of misclassification error, this thing is completely dead. This is number 34, right? There we go, number 34. If I look at the misclassification error for this guy on the training data, I see he's going to be 1 minus 78, so let's call him about 22%. Right, so he is only getting, we have a better marker. There is a black one? Oh, behind the green one. Does it work? Yep, cool. Okay, so what is that? 22% of the training data is misclassified? Yeah, 22%. Okay, so not surprisingly, the small tree is doing worse on the training data, but what really counts is how well it does on the test data. And it turns out this small tree actually does slightly better, right? 28%. So that's my misclassification error for test on this one is 28%. So again, the fact that it does worse on the training data is not surprising because it's a much smaller tree, a much simpler model. But the fact that it does sort of a little bit better on the test data might suggest to me that this model might be preferable. Now I know, I mean, these numbers are close. I haven't done any sensitivity analysis. I just took one, holdout sample, so we could argue about this. But at least they're comparable. And in fact, I might favor the smaller model because of that. They're comparable, and generally parsimony suggests I should favor smaller models. If you want to see the fit, well, it's not very exciting, right? It's just a single split on V11, right? 79 observations go here, and 51 observations go here, and that's it, right? That's your fit. So you can see the picture of it. Again, not exciting at all. Just a single split, right? 2 terminal nodes. That's all you're doing. But it's interesting that that simple model, where it just found one variable to split on, actually does better on the test data than the default tree. Slightly better, arguably better. Okay, so that shows you a little bit how you can override some of the defaults. Now, what's interesting, though, is how these defaults sort of affect you in some way. Suppose I said, okay, so this was a depth 1 tree. Here, I'm not going to store it as anything. Let me just fit a depth 1 tree and see. So there's the depth 1 tree. Then I can go to depth 2 and get that. And here, let me plot these so that's easier to see. But at some point, it's going to refuse to make them any bigger, even if I tell it max depth equal a larger number. So there, okay, that's depth 2, 1, 2. I can ask for depth 3. I have it 1, 2, 3. I can ask for depth 4. Do I get it? 1, 2, 3, 4. But I think at some point it's going to refuse. 1, 2, 3, 4. Yeah, it's not going to grow it bigger than 4. So I have to actually change more defaults if I want to grow a bigger tree. And so that's what I did here on this last part of this example. I went in and got, I think these are almost all of the values that you can set. So there's a min split criterion, there's a min bucket criterion. I know min bucket is like the smallest number of observations that it will allow to be in any terminal node. This is some sort of cross-validation criterion that should be positive, so I set it to be negative. There's a max compete. All these things, I sort of zeroed them out. And then tell it max depth 6. And this will actually get it to fit a tree of depth 6. And if you don't believe me, here's the syntax. And again, you can do help on all these different parameters in rpart.control, but there is the tree of depth 6. If you don't believe it's a tree of depth 6, I can plot it for you and text it. And you can see, well, that's a mess, right? Let me just plot it and not text it. So you can see this has depth 6 because if you start counting splits and you go deep as you can, 1, 2, 3, 4, 5, 6, right? So this is a tree of depth 6. It's not surprising that it has 100% accuracy on the training data, right? Not surprising because it's a very complex tree. And so that's why R was sort of resisting me before when I was trying to grow the tree bigger and bigger, because I was pretty much, fitting everything perfectly, and here I am fitting it exactly perfectly. I have 100% accuracy on the training data, which of course I don't really care about. But it's also interesting that this one also has 73%, so a little bit better actually than the other 2 trees I looked at, even though it's bigger. It actually gives me, 26, 27% misclassification error rate, which is actually a little bit better than both of these. Although, arguably it's comparable, and I would be hesitant about fitting a tree this large. But, if you wanted to, this would be how you would do it. And whether or not it's really doing better is suspicious. Of course, the fact that this is 100% tells you nothing, but 27%, it's not that bad. If I am overfitting, I certainly haven't done it that severely, and it's not that much worse than the default. So that shows you a little bit about rpart. I'll give you some insight into how the algorithm is working, but I just wanted to show you the syntax and how you call it. Any questions on anything I've said so far? Okay, so let's talk a little bit about what's going on with these algorithms. So I don't think you have to be sort of an algorithm person to realize this. It's not searching over the space of all possible trees, right? You wouldn't want to do that. There's a lot of trees that you could grow. If you think about the sonar data set with 60 predictors and splitting each one of these on any value, well, it's too many trees to consider, right? So it's doing sort of probably the first thing that you would think of as sort of a top-down approach, a divide and conquer approach. And this gets called Hunt's algorithm a lot in the literature, and you can read on page 152 about it. Basically what you do, you start at any node with the set of records that you have. If all those belong to the same class, you stop. It's a terminal node. If they have records that belong to more than one class, then you split on it according to some criteria. And we'll talk about what criteria we use, but basically this is the top-down approach. You might say, well, that's the obvious thing to do, but you could think of other approaches, right? You could think of searching over the space of all possible trees to maximize some criteria. You could also think about starting with the single observations and sort of joining them together until you get, so there's different things you could do, but this probably is what would come to your mind first. This is the top-down approach. This is known as Hunt's algorithm. So let's sort of think about how you do this one here. So this is this example of cheating on your taxes. And if you think about these guys, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and they go no, 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 4 no's. And then, let's see, 5 is a yes, and then 8 and 10 are yeses. Okay, so this is no, no, no. Okay. So then the first thing you do is, by default, right, if you had no tree at all, right, a tree of depth 0, you would just say they don't cheat, right? Assuming you have equal loss, then you just say, I'm going to go with the majority class and say people don't cheat. Okay. Then after that, it's not homogeneous because it's not true, right? There are people that cheat, so you split on that, okay? The first thing that we split on here, and we'll talk about how we chose what to split on later, but suppose we first cheat on refund. Okay. So if they ask for a refund, yes, that's 1, 4, and 7. None of those guys cheated. Everyone who asked for a refund, 1, 4, and 7, did not cheat. So 1, 4, and 7 go in this I asked for a refund category, so this with the black square becomes a terminal node. And then the other 7 guys stay in the don't cheat category. We're not done with them yet. We still can consider splitting them, but the don't cheat people we're done with. Okay, so then we go, sorry, the refund people we're done with. Now we go to the no refund people, okay? So these guys we're done with, the yes refund we're done with. The no refund people, we're gonna split them, and we're gonna split them, suppose, on marital status, okay? So we can take the single and divorced people over here. Now the married people, okay, who's left here? 2 is married, he didn't cheat. 3 is single, okay, so 5 is not, okay, 8 is not married, okay, so 9 is married, he didn't cheat. So it looks like everyone who's says no refund and is married didn't cheat, right? No refund and is married didn't cheat is 2, also it's not 5, it's not 8, it is 9, right? All those guys, right? They said no refund and they're married and none of them cheated. Okay, so that again is another terminal node because it's homogeneous. So now we're just left with these 1, 2, 3, 4 people, and we need some way to split them because it's not homogeneous, so we consider splitting it. And we need some way to separate this guy from the other guys, so it turns out we can use their taxable income, right? Because number 3, he made 70,000, whereas 5 made 95, 8 made 85, and 10 made 90,000. So if we just take people that made, here it says less than 80K, right? Less than 80K, that guy's the only one who made less than 80K. So he goes over here into the don't cheat, and the other 3 guys go into a terminal node that's homogeneous, but with respect to cheating, all 3 of those guys cheated. So in this way, you sort of divide and conquer until you get to terminal nodes that are homogeneous. Now, of course, the actual trees, we don't grow down that far, but that's the direction we're going in. We're pushing towards homogeneity in all the terminal nodes. And once you get there, of course, you have to stop. So that's sort of the top-down approach. That's Hunt's algorithm. It's done, again, in this greedy fashion, where at each stage you do, well, it's usually done in a greedy fashion. At each stage you do what's optimal. That means that you don't really look ahead. So this may not be optimal in the end, even for the same criterion that you're trying to minimize. And there's an example on the homework where it turns out if you start with a suboptimal split, you actually wind up with a tree that turns out to be better than if you do the optimal thing at each stage, right? Because the optimal thing at each stage doesn't lead you to the global optimum. And so this is not guaranteed to find the best tree in the whole universe, but it's sort of efficient because you just do the greedy thing. You just do the optimal thing at each stage. And that's what I said last down here. It's computationally efficient, so it tends to be popular. Now, once you say, I'm going to use Hunt's algorithm, I'm going to use this greedy approach, there's still some questions you need to answer. So in particular, what type of test conditions should you consider, right? If it's a continuous attribute, how should you split it? If it's ordinal attribute, how should you split it? What criterion to use to select the best split, right? How can I say this split is better from this split? How should I know if I should split on this one versus this one? And then when to stop. Okay, so for number 1, that's sort of easy. I'm going to match what R does, which is to only use binary splits for both numeric and categorical predictors. So categorical predictors, I'll just put some classes on one side, other classes on the other side. For numeric predictors, I'll just choose a split point. We usually choose like a midpoint between 2 numeric values and use that as a split point. Everyone less than it goes one side, everyone greater than it goes the other side. Number 2, common things to consider to measure how pure the nodes are classification error, the Gini index, which is popular in statistics, and entropy, which is more popular in machine learning. Then for number 3, we're going to say that for next time because that's sort of tricky. That really gets into the idea of model selection. How deep should you grow the tree? How big should the tree be? You don't want to overfit, you don't want to underfit. It's sort of a tricky question. And it actually turns out that what people do, and we'll talk about it next time, is they actually grow large trees and then cut them back. And that tends to work a little bit better than just sort of choosing the right point to stop. Just grow a larger one and then figure out where you should have stopped sort of in retrospect. Okay, so with regard to question number 1, how should these splits look? Again, R just does binary splits. The book talks about multi-way splits, sports, luxury, and family, but R is always just going to do binary splits, so we have to put some of the classes on one side and then you just put the other classes on the other side. So the car type could be sports, luxury, or family. Now, ordinal, arguably you might not want to split and break the order, right? So small, medium, and large could be legal, or medium and large, and then small could be legal, but it's questionable whether you really would want to do small, large, and medium. However, excuse me for paging through slides here, but if you look back at one of the examples we had, right, it did old, young, and middle, right? Arguably you wouldn't want to do that, but R does it. I'm almost positive there's no way to tell our part not to do it without sort of doing something pretty creative. So we'll allow it, but maybe you want to feel a little bit guilty about it because arguably you don't want to do that. Yeah, I mean, because it's ordinal, right? So you're not taking quadratic transformations of your numeric things, so arguably you wouldn't want to allow your ordinal things to sort of break like that. But there's really, you can argue either way, whether you should allow this or not. R allows it, some people don't like to allow it.
I don't know, I mean, it seems to me that you make the assumption that if you're not allowing it, that your data is essentially linear at that particular spot.
But I mean, arguably that's what we're not transforming the numeric things, so that's sort of what I'm. Yeah, reasonable people could disagree on this, I think. And the other thing you could say is, well, sure, if you don't allow it now, you can always split on it later and break that one out later. So it could happen anyway, right? So yeah, that's not too big a deal, but you can think about whether or not you want to allow that. And then for numeric things, the real question comes up is where should the split point be, right? If you have one observation at 90 and the next lower one is at 70, usually people use midpoints, but sometimes people do some more careful interpolation. And of course, it doesn't matter on the training data, but it's going to matter on the new data, which is really what you care about. So for numeric data, you choose a single split point, and you're either less than it or you're not less than it. In this case, greater than it or you're not greater than it, and that's going to determine how you split the numeric attributes. So these are the types of splits that our part allows, and so we'll sort of go along with this. But different people disagree on this. Some people allow multi-way splits. Some people allow some things and other things. Some people allow a split for every value of the categorical attribute. So anyway, we'll just sort of match what R does here. Then the next question is, how do you measure how well your splits are doing, right? How do you know if I have to choose between splitting one way or splitting another way, how do I know which way is better? Well, the obvious thing you could look at is, what is the misclassification error? Compare the two in terms of misclassification error. And so, for example, misclassification error here, this is sort of a general form of it, but for two classes, right, if the majority class was 70%, then 1 minus 70%, you'd have 30% misclassification error. So that's the obvious thing to do, but it turns out people don't like to do that. Other popular approaches are the Gini index, which is to take each probability for each class, square it, sum them up, and take 1 minus that, or the entropy, which is p times log base 2 of p summed up with a negative sign. So these are common approaches. I think I'll go into detail on these next time, but basically Gini index is what our part is using, and entropy tends to be what things like C4 or 5 are using. You can correct me if I'm wrong, but I'm pretty sure on that one. So let's talk about misclassification error, for example. So this is generally our final metric, right? In the end of the day, we judge the model based on how is the misclassification error on the test data. So it makes sense we might use this as our criterion. I'll talk about why it also makes sense we might not, but arguably you could say let's just use misclassification error. It's simply the fraction of total cases which classified, and also we used accuracy interchangeably. 1 minus the misclassification error is the accuracy. So let's sort of take a simple example here. Before I do this one, before I get into this example, let me frame the problem a little bit just to contrast these three. So I wanted to just mention to you a case where they differ. See if do I have it here? Oh, maybe I don't see it. Okay, I'll talk about it next time. I'm going to give you an example where they differ. Question?
I'm going to convert about misclassification error.
Right.
So when you, at each layer of the tree, when we select the best play, it's not terminal yet, so there's no final classification
Right,
yet.
right.
So where's the classification error?
Right, so we look at basically the reduction in the misclassification error as if you were to sort of stop there, right? So we're just being greedy. We're just being greedy. So, you say, should I split here? Well, how much is that going to reduce the misclassification error for now? But you're right, it's not the terminal node. And so, does that, maybe it's not helping. Maybe, well, I'll go through some examples and see if this comes up.
Measured on the entire tree, right?
Right. So, and I mean, but the same question comes up with Gini and entropy, right? You calculate the Gini or the entropy within a single node, and then you take the weighted average across the terminal nodes to calculate the overall.
You mean assume if the non-terminal node is going to be classified as just one single value?
Right. So you go with the majority class in there, and then that becomes, okay. So we'll do some examples, and if it's not clear after that, let me know. Okay. Should be clear. So let's start with this example, right? So we'll start with misclassification error, because that's what you asked about anyway. So this case here, we have 3 attributes, A, B, C. Now, once you pick the attribute, there's no choice about how to split, right? Because each one is either true or false. So, normally I would have to pick the attribute and where to split the attribute. But here I just say, okay, I could split on attribute A, true, false, B could be true or false, C could be true or false. Okay. And then you see the number of instances for each one. The 2 classes here are plus and negative. You can think of +1 and -1 in the case of sonar. And so this is actually a problem that I just got right out of the book. And it says, according to the classification error rate, which attribute would be chosen as the first splitting attribute? So what's really going on here, right? There's actually 25, 100 things, right? So you start with 100 things in your terminal node. And you can either go and do A equal true, or A equal false. That could be your first split, okay? You could do B equal true, or B equal false. That could be your first split. Or you could do C equal true or C equal false. That could be your first split. And so the question is, how do you decide which one you want to do? Well, you could look at which one reduces the misclassification error the most at that point. You could look at which one reduces the Gini index the most, or which one decreases the entropy the most. And so this problem specifically says, use according to classification error rate. So we'll see which one decreases the classification error rate the most. So the first thing to note is that initially, misclassification error is at 50%, right? Because if I had to pick the majority class here, well, 25, 20, there's 50 here and there's 50 here, so it doesn't matter. Either way I do it, I'm going to get 50% error initially. So initially, I'm at 50% misclassification error rate, right, in the initial node. So that's the misclassification error initially before I start splitting it all, 50%. So then we just want to see how each one of these does. Well, if I look at A, right, so let's see. A can either be true or false. Oops, there's that one, true or false. And this is A equal true, A equal false. It looks like there, let's see, for A equal true, I have 5, 25, looks like 25 here. And for A equal true, 0 negatives. Then for A equal false, I have 25 there and 50 on the other side, A equal false, 25, 50. Yeah, so there's my 100. Okay, so if that were my split, what I would do is every time A equals true, right, I would call this the plus class because it's actually homogeneous, right? This node is actually perfect. I would stop right there. That one's 25 to 0. That one I would call the plus class. This one I would call the negative class, right? Because it has 50 negatives and 25 positives. So I would call this one the negative class, and I would be getting these 25 wrong. These 25 wrong. So this one would give me a misclassification error rate of 25%. So my delta, if you want to think about it in terms of delta, is 50. I went from 50% down to 25%. So my delta for A is 25%. So splitting on A gives me a reduction from 50% down to 25% if I'm using misclassification error as my criterion. We could also talk about using Gini and entropy, but for now we're talking about using misclassification error rate. Okay, you could also do the same thing with B, right? B goes plus minus, it's either true or false. I split on B. I think for B true, there are 530 here, and I think B true, there's 20 negatives. And then for B false, there are 20 positives. And for B false, there are, should be 30, right? 30 negatives. So if I were to split on B, then I would have to say, well, this would be B equal true would be a positive class because it's 30 versus 20, so I always pick the majority. This would be a positive class, and this would be the negative class by getting this 20 as well as that 20 wrong. Okay, so I'd be getting 20 wrong, I'd be getting 40% wrong, so I'm going from, so the misclassification for splitting on B would go to 40%, so if you want to use delta, your delta is 10%, right? You went from 50% down to 40% if you split on B. So I'd much rather split on A over B if misclassification error rate is my criterion. Okay, and then finally that leaves C. So C plus minus either true or false. And so with C, this is easy because they're in order. I get 25 positive when it's true and 25 negative when it's true. So that's 25 and 25. And then when it's false, I get 25 positive and 25 negative. So C is absolutely useless, right? I went from, it doesn't matter which one you call this or which one you call this. There's no majority in either one. Either way, you're going to get, 25 wrong in each terminal node. So you're going to go from 50% to 50%. So C gives us no information. This classification error rate equals 50%. And so your delta is you've gone down 0. Now, I think this is the one in the book. I have to check. Where it actually turns out, though, this is where you get in trouble for being greedy. Because if you split on C eventually, then on the next split, you can do perfectly. So it's sort of a cute example for that reason. But if you're being greedy, you don't want to split on C initially because it buys you nothing at the time. But in the long run, it actually turns out that C works better. But these algorithms are always greedy. So that's the story when you split on misclassification error rate. Now, it turns out that you can get different answers when you split on some of the other criteria, being whether you split on Gini or entropy. If you think about these things are using extra information about how pure the node is other than just how many are classified as a majority class. And arguably these things give you a smoother criterion and use more information. So again, actually people prefer these statistics. We often use the Gini index. Entropy we often use in machine learning. I think C45 was famous for using entropy. They're very similar, and we'll talk about the comparisons. But you can get different answers depending on which one of these you use, and we'll see sort of how they differ. But both of them are trying to sort of balance this trade-off between, ideally what you want is you want a split that gives you sort of two large classes, right? So you want both nodes to have a lot of things in them, and you want both nodes to be homogeneous. Given that you can't have a perfect 50-50 split and both of them be homogeneous, you have to sort of trade off the fact that, can I break off a small fraction and have that be homogeneous versus break off a large fraction but not have it be quite as homogeneous. So you have to trade off sort of the homogeneity with the fraction of observations or the balance of observations between the two terminal nodes. And so these different metrics do it differently. I went through an example with misclassification error today, but on Thursday I'll go through an example with Gini and entropy. Also on Thursday, I'll finish up that. We'll talk about sort of the class imbalance problem. We'll talk about the area under the curve. We'll talk about that issue number 3, which I didn't get to today, which is how do you know when to stop fitting? And I'll tell you a little bit about what our part does. That'll sort of wrap up chapter 4. And then next week, which I think is probably going to be our last week, I'll get into some other algorithms for solving the classification problem, such as nearest neighbor, support vector machines, bagging, boosting, all these sort of popular things that are much more effective. But once you sort of have the background and you sort of understand one algorithm well, you can appreciate how the others work and how they relate to it. And we'll do those next week. So any questions before we take off? Yes?
I'm just curious, is there like an algorithm over there, like using greedy, but at the same time maybe look one step ahead?
One step ahead. I'm not familiar with a specific one, but it'd be simple to think of, looking a one step ahead or a two step ahead. Again, what they generally do, though, the most common implementations I've seen are just take a greedy approach and then prune it back. So in that way, you have looked ahead at least along one path, and then you prune it back. Some other people sort of will do like random initial starts and sort of put some randomization in there. There's different algorithms. I think other people here may be more familiar with some different algorithms than I am. But the greedy approach tends to be sort of the approach that dominates. The fact that it's suboptimal is sort of not that worrisome because you're not really trying to do the optimization on your training data anyway. So if you really wanted to do some intelligent optimization, you might actually want to do something with holdout data, because optimizing the training data really isn't the end goal anyway. And if you optimize it too well, you might actually be overfitting. So people haven't sort of thought too much about how can I optimize this loss function on this training data, so much as how can I fit a good classification model that will validate well on training data, on test data. And sometimes the things that work well on test data actually tend to be things that are a little bit suboptimal, because that makes them less sensitive. Okay. All right, any other questions before we take off? Okay, oh, one last one.
I was just wondering if you're going to go over like the intuition behind Gini index and...
Well, I mean, so, yeah, so I'll write them as a function of p for the two-class problem, and you can see that the Gini becomes simply the binomial variance. It becomes like p times 1 minus p. And then the entropy, there's sort of a strong motivation that you can actually come at from gambling in a lot of other ways. I won't say too much about it. I mean, they're both measures of homogeneity, and sort of one of them is steeper near 0 and 1 than the other. So I won't say too much about it, but I'll discuss a little bit next time about why they differ and why some people prefer one or the other. But I'm not really an expert on that, but I'm aware that there's differences, and people give strong arguments for either one. Okay, any other questions before we take off? Okay, see you guys Thursday. Or Friday, sorry, Friday.